I know it's a total kludge, but I had to do it because I don't have a drill big enough to fit that, to mount that switch through. So as you can surmise there, I've got the LiPo wire coming out going to the switch, and then a big fat black wire coming out going to the terminal block down here. And so thus there's my break in the voltage from the LiPo battery. And I can just switch it. It's pretty solid. I've just got some good old electrical tape protecting the contacts, but it's pretty solid. Actually, I had really good thermal capacity with the iron. It's an old Radio Shack soldering iron, but it has been amazingly good. When I first bought it, I was a little ignorant on, I didn't do my research, and I was a little ignorant. I bought the Radio Shack one, but I'll be darned if this thing hasn't turned out to be really good. And thermal capacity is very high, and you know, you can always turn up the heat. So I turned it up to 730 degrees Fahrenheit, and I was able to handle I guess 8 gauge wires fairly well. I guess there's nothing you can't solve with enough heat. Nothing you can solve with enough heat. So there we go. He's in place now. So I may tie wrap him somewhere just for additional stability. Probably tie wrap him to that post there. And so now all we have to do is wire up the Arduino, and then I can start my programming. Let's do that. Well, we got a problem. I'm troubleshooting. We've got the Uno. It's all hooked up. Got its wires hooked up to the motor controller. Not warm? No. And no matter what signals I put out here, and I've been scoping them to make sure they're the right values, that I am getting signals there. I'm not getting any action out of this motor control board. Don't know what's going on. I may have to play with this one. I've got this spare here, play with this one outside of it just to see if I can get it working and see what the mechanics involved here is. Everything else is working. The power supply over here hidden behind all these wires, he's working good. The terminal blocks are working. The LiPo battery's working. My LiPo battery watcher is working good. No buzzers going off yet. I'm still maintaining 5.1 volts at my output, and so all of that's good. But the board that I built this around, that I went to all this trouble to rearrange everything, is not working. So I'll be doing some troubleshooting. If there's any interesting troubleshooting, when I put this on a breadboard and start playing with it, I'll show you some of that. If there's anything interesting there, maybe we can do that together. But we'll go to the next step here and start troubleshooting. Well, it started working, and what I did, was I put jumpers on the board. Let me get the board out. There's 2 enable pins on the board. I know you can't really see the detail on this, but basically there's an enable A and enable B here. You can see those jumpers that are there that are already in place. I put those jumpers back, and instead of using Arduino pins, let's see how close I can get there without, yeah, you can see those jumpers. This jumper, enable A, enable B, motor A, motor B. So I went ahead and put those back, and so that it was permanently enabled, and then just used the the PWM pins, the pulse width modulated pins, to turn it on and off, turn each motor on and off. There's motor 1, there's motor 1, motor 1, motor 2, motor 2, and then you use the combination of those to stop it, reverse it. You can put on dynamic braking. You can use loose freewheel braking, whatever you want to do there. And basically, very simple coding in Arduino. And by doing that, and all I did was set one motor to reverse and one motor to forward. This motor is going in reverse, and the other one's going forward. Guess I don't need to prove that, but he's going forward down there. But at least it shows that's working. So now it's just a matter, oops, excuse me again. Now it's just a matter of coding. And I've got these extra wires that I don't have to enable the things, because it's probably going to go at this speed. I don't see myself PWMing these, enabling or disabling these. This is pretty slow, so I'll probably just leave those jumpers in and then just determine speed, or rather determine direction by the other middle pins there, the enabler pins in the middle here. So that would mean I can control the direction of this thing and where it's headed with only 4 pins. And that leaves all the rest of the pins to do what I want to do with, which is getting back to the ultrasonics board. So that's where we're headed. We're still headed toward the ultrasonics and the display board. But this looks good so far. It looks like we can do some controlling. And I've got a kludgy switch. That's the one thing I don't really like. I'll get that fixed. The rest of it's okay. The wiring looks about like what my wiring looks like, all over the place, but I can neaten it up a little bit. But as soon as you neaten up wiring, as soon as you neaten it up and put tie wrap it and make it look all neat, you have to clip a tie wrap off and do something with it. It's what I found. And so it's almost useless to do that. And I've been monitoring the voltage the whole time, and it's really good. It's pretty solid. 5 volts, 5.1 volts, with the motors running or the motors not running. And so we're doing good. I think we're doing okay right now. And so next step is to do a little more control testing of the motors, and then we start heading toward the ultrasonics. And, getting that connection going to where the ultrasonics can talk back to the control board and tell it which direction it thinks it needs to go. I apologize if you get those horrible lines, but I was just going to show you the Arduino code. Very simple. I set pin modes on pins 2, 3, 4, 5 as your outputs for the motors to tell them what direction to go, and then 9 and 10 are the PWM. Well, the 9 and 10 really are not needed now because they're jumpered on the boards themselves, on the motor control board itself, as I showed. And then I come down and do an analog write of 9 and 10, which is really not necessary anymore. I've really got to take that code out, actually. But I do a digital write of 2 and 3 of low and high, which will set the direction of the motor. So pins 2 and 3 go into, say, motor A. Low and high will set it forward. High and low would set it backward. And then I do pins 4 and 5, low and high, which sets it forward. And then I switch it, 4 and 5, high and low. So I went low and high, and then high and low, and it goes forward a little bit and then goes backward a little bit. And we can see that. You can see that. See how that thing's going forward and backward as those pins switch from high to low to high between pins 4 and 5. And so we're working. We're working, you know, in terms of control. We're working. And I always go the other way with that thing. We're working in terms of control anyway, and so now we got to get to the, like I said before, to the ultrasonics board so it can start telling this board what to do, or sending it back, at least sending it back the distance and position so that it will know what to do, what direction to go. Okay, that's where we're headed. Well, I'm putting together the VCO, the voltage controlled oscillator, just as to play with. It's this LM2917. I'm sorry, 2907. Well, no, it is 2917. Need my glasses. And so I'm putting it together with using this circuit on the data sheet, the official data sheet. This is more for a tachometer, but you know, it'll do. So I'm getting the circuit, getting the components together now to do it, and where I am putting it together is right here. Not much to see right now. I've got the come on, focus in. I've got the frequency generator hooked up, and that is it. That's all I've got right there. And that little IC, the little 8-pin IC, is the VCO. And just to make sure that my, well, as you can see, I didn't clean up my desk this Labor Day. But just to make sure that my frequency generator, which is there, sorry about the light, frequency generator, which is set for 10 kilohertz, I don't know if you can see that or not, but 10 kilohertz sine wave, and about 3.3 volts peak to peak, just to make sure that, keep it honest. I'm measuring it also on the scope, and that is what it is. So I will get back when we get a little further down and get some more components on that. And why am I doing this? This has nothing to do with the robot, but it's fun. I love building circuits. Don't you? I wanted to show you these Joe's, well, actually these are E-Projects. There's some called Joe's Nose Electronics that are the same. This particular one's called E-Projects, but these are really ingenious ways to package electronics. And this one is 31 values, 775 pieces. The E6 type, you know, resistor kit, all of the E6 values, 10 ohm to 1 mega ohm, and you open it up. You may already have this, you may already know about this, but if you don't, you open it up and they have these things beautifully categorized. 10 ohm, there's 10 ohm, then it goes to 15 ohm, 15 ohm, and 22, 33, and you look, because I need two 5Ks according to the diagram. Well, it's not going to be a 5K because this is E6 value. But I've got 4.7K, so I can just use two of these 4.7Ks. It'll be close enough for what I'm doing. So I can peel a couple off of there. There's my 4.7K. Put it back down in the package. Put it back down where it was. Keep your nice, neat little pattern. And you can just search real easy all the way up to 1 mega ohm. Put it back in your box. I just wanted to show you that. They're not expensive either. I don't remember the price of this, but you can get them on Amazon or eBay, and it's E-Projects, and or it's eprojects.us, and you can get these for a pretty good value, if I remember correctly, and great way to store your resistors, and then when you run out, well, you just order another one, I guess. But anyway, back onto the VCO. Well, it's actually working. I had to substitute a few components in there that I didn't have the exact value to, but my eProject boxes and Joe's Nose boxes, I had the right values, or close to enough. This is a Joe's Nose. This is a Joe's Nose capacitor bag, 0.047 microfarad, 0.47 microfarad, and I had to use two of those in parallel because I didn't have a 1 microfarad. So anyway, it seems to be working, and I won't show you the circuit anymore. Nothing's really going on there. But on the, I wish I could show you both at the same time. I don't have a split screen. But on the, as you can see, on the, let me get that a little better light. That's 0.4, that's nearly half a volt, 0.447 volts. And I'm sitting at, let me just swing and show you that. I'm sitting at, you see that 100 hertz? They're at the top, and I'm sitting at 100 hertz. I focus in, this thing takes the longest time to focus in. I'm sitting at 100 hertz. So, what is that? Oh, that's just nothing. So at 0.466, I'm at 100 hertz, and I'll just call out what I'm at. If I go to, there I just went to 110 hertz, and you saw it jump up to 0.49 volts. If I go to 120 hertz, it goes to 0.53 volts. So I'm putting in a frequency into the VCO, getting out of voltage. So voltage or frequency to voltage converter. I think I called it the other way around, but this is a frequency to voltage converter. So I'm at 130 hertz, and we're at 0.58 volts. So let's jump up, all the way up to 250 hertz. As you can tell, this particular circuit, which is a tachometer, variable reluctance magnetic pickup, or tachometer, it's used to dealing with lower frequencies. I'm sure with proper component configuration, you can deal with much higher frequencies than this. But at 250 hertz, we're at 1.1 volts. And if we go up, just how high can we go before we reach our, you're supposed to power this with 15 volts, and I'm powering it with only 5 volts. So we're going up to close to, well, it looks like we met our maximum there. We met our maximum voltage at about 800 hertz. So I go up to 800 hertz, we go to 3.5, roughly a little over 3.5 volts. Probably, like 70% of your VCC or something, some sort of rule of thumb like that is what it goes to, and that's why they want you all the way up to 15 volts. The reason why I don't put it up to 15 volts is I've got some servos hooked up to this breadboard, and I just didn't want to disconnect them, and I don't want to burn them out. So 5 volts I figured would work, and it's working for demonstration purposes. But it's working. We can see that the VCO, now I'm going to go back down, and there's 570 hertz, and we're at 2.5 volts. Isn't that fantastic? I love that. Now let's see, what could we use this for? Well, we'll have to figure out something to use this for. It's really easy to put together. It's just some wires and 1, 2, 3, 4 components. And you have a good, albeit low frequency converter. Frequency to voltage converter, but we can change out the components. I know along in the data sheet, this is one I'm using right now for the variable magnetic reluctance pickup, which is going to be low frequency. I know that somewhere along here will be a higher frequency pickup data sheet. There's one that I almost put together, but that would have been the wrong one to do. That was a speed, almost like a speed detector, where it would turn on at a certain speed. Very interesting though, very interesting. It makes good reading. Some good reading up here, application information. Lots of graphs and charts to show you its the performance. I probably should have looked at some of the charts. I didn't. I just wanted to get the circuit together and get it working. Voltage gain is 200 volts per millivolt. Output sink current 40 milliamperes. Output source current 40 milliamperes or 10 milliamperes. And not bad. It's not a bad little chip. And I don't really see much more. Those are just the different packages. What did that say? Doorbell? Automotive door lock control, clutch control, horn control, touch and sound switches, handheld tachometer, yeah, I can see that. Speedometers, frequency to voltage conversion, over under speed sensing. Yeah, that was the first one I almost built, was the over under speed sensing. But there's the description for those of you who are interested. That's interesting. Monolith frequency to voltage converters with a high gain op-amp comparator designed to operate a relay, lamp, or other load when the input frequency reaches or exceeds the selected rate. The tachometer uses a charge pump technique and offers frequency doubling for low ripple full input protection in 2 versions. And its output swings to ground for a 0 frequency input. That's interesting. And then blah blah blah, it goes on, talks about the comparator. But anyway, I thought you'd find that interesting. Hopefully you found that interesting, and I certainly did. Building it was a little bit of an excursion from what we're doing, but fun nevertheless. And there's just a panoramic of my humble lab gear, and we will see you next time. Thank you. Okay, with the new DC to DC power supply in and the new motor control board that does not sit on top of the Arduino, this gives me plenty of pins now to communicate with the display board, the display/ultrasonics board. There it is, running into the couch, as you can see. And he's just running a hard-coded course right now. No ultrasonics or anything telling him where he's at. But with now that I have that, now I can mount the display board, the ultrasonics board, and we can get some communication back to this board and to the control board, Arduino control board, and make some intelligent decisions on where he wants to go. And so finally we're back to where we were, kinda, yet we're a lot better off now that we have a free Arduino that both is controlling the motor and yet has lots of pins left over to talk to other boards and make better decisions. Woohoo! Look at there. He's traveling. And look at that. The weight, the extra weight on him, doesn't matter a bit. Those motors can handle it. That's what I like.